Hello everyone, my name is Signolo. Welcome to another video by Attention Matrix, where we try to make learning fun and easy. Please comment, like, and subscribe if you would like us to continue making this content and you enjoy it or find it helpful. Now on to the next video. Let's get right into it. Okay, welcome to our next video on momentum. In this video, we will be covering elastic and inelastic collisions. We will be explaining what elastic collisions are and what inelastic collisions are and how you differentiate between the two. And we will cover a couple of important points and aspects that you should keep in mind while solving problems regarding elastic and inelastic collisions. Okay, let's jump right into it. Firstly, okay, we've got two different types of collisions when we're looking at our topic of momentum. We've got elastic and inelastic collisions. But before we actually get to looking at what elastic and inelastic collisions are, I want to look at what collisions are. Okay, let's just look at what collisions are before looking at what makes them elastic or inelastic. So what are collisions? So if you've got, say, a ball, right? A ball that's moving in that direction. I mean, you've got another ball that's moving in this direction. When these balls meet, right, they will impact one another. They will strike each other with a certain force, right? Both balls have certain momentums, right? Each ball has its own momentum, and while they're moving at that momentum, when they hit one another, they will strike one another at a certain force, and so basically they will collide. Okay, so that is what a collision is. It's when two objects impact one another, or it's when two objects strike one another, or when one object strikes another object. Okay, so for us to have a collision, we don't necessarily have to have both objects moving. So for us to have a collision, only one of the objects could be moving. So for instance, if you've got a wall and you've got a person standing there, okay, and this person happens to have a tennis ball, they throw that tennis ball towards the wall, and the tennis ball hits the wall and bounces off the wall. Right, now that there is a collision. As soon as that ball strikes the wall, that is a collision. Now in this instance, the first object is the ball, the tennis ball, and the second object is the wall. So not both objects have to be moving. Only one can be moving, or both of them can be moving to make contact, to collide. Okay, so this also counts as a collision. As long as you have two objects impacting one another with a certain force, right, then you have what we call a collision. Okay, so this also counts as a collision. Now, what makes an elastic and inelastic collision? What makes a collision elastic and what makes a collision inelastic? Let's start with an inelastic collision. What makes a collision let's start with an elastic collision. What makes a collision elastic? Okay, so elastic. What makes a collision elastic? Well, I'm going to go back to using the ball and the wall again. Okay, I'm going to redraw that person there. The person has a ball. They throw the ball towards the wall, right? There's the wall there. I'm going to redraw it again. And there's the person there throwing the tennis ball. The ball hits the wall, and the ball bounces off the wall and moves, and it bounces off the wall and moves away from the wall. Now, this ball here has a certain energy. It has a certain energy. Okay, this ball here, as soon as this is one and the same ball, right? This is one and the same ball. It's the ball before collision and the ball after collision. So before collision, this ball has certain energy, a certain amount of energy, and after it bounces off the wall, it has some energy as well. Now, what makes a collision an elastic collision is that the energy after the ball collides with the wall is the same as the energy before the ball collides with the wall. That's what an elastic collision is. Remember what a collision is. A collision is when two or more objects collide. It's when two or more objects strike each other. Now, before they strike each other, they have a certain amount of energy. After they strike each other, they have a certain amount of energy. If those two energies are the same, then we have what we call an elastic collision. Okay, so but you might be asking yourself, okay, cool. So I get that it's when both energies are the same, but what kind of energies are we dealing with here? What energy do we have here in this system that we're looking at? Well, if you're looking at this ball is thrown towards the wall, right? This ball is thrown towards the wall, so it is moving with a certain velocity v. It has a certain velocity, right? And it bounces off the wall. As soon as it bounces off the wall, it is moving away from the wall with a certain velocity. Now, which kind of energy has to do with velocity? In other words, which kind of motion has to do with motion? Which energy gives us a measure of motion? Well, that is our kinetic energy. That's our kinetic energy. Okay, it is our kinetic energy. Okay, so in other words, this ball here has a certain kinetic energy before it collides with the wall. Before it collides with the wall, it has a certain kinetic energy. It collides with the wall and then it moves away from the wall with a certain kinetic energy. Now, those two kinetic energies in an elastic collision, those two kinetic energies are the same. Now, what is the equation for kinetic energy? We'll remember from previous grade that the equation for kinetic energy, EK, is equal to half mass of the object times the velocity squared of the object. Okay, this should be provided to you in your formula sheet, so there's no need to memorize it. It's a simple equation, it's easy to remember, but I recommend to always copy your equations from your formula sheet in order to reduce the risk of making a mistake. Okay, so that is kinetic energy. So the kinetic energy of this ball is the same. So you have your kinetic energy before, right? Kinetic energy before the ball strikes the wall, and you've got your kinetic energy after the ball strikes the wall. These two kinetic energies are exactly the same, and that is what makes your collision an elastic collision. Okay, now what makes an inelastic collision? You can probably guess then what an inelastic collision is. Let's redraw that scenario again. So you've got that same person there. Person throws the ball, the tennis ball, towards the wall, right? Person throws the tennis ball towards the wall. Now, the tennis ball hits the wall, bounces off the wall, and moves away from the wall. The ball has a certain initial velocity before bouncing off the wall, and it has a certain final velocity after bouncing off the wall. Now, when the ball bounces on the wall, right? When the ball makes contact with the wall, you will agree with me, if you go outside right now and you throw a ball against the wall, you will agree with me that you will hear a sound, right? When the ball makes contact with the wall, it will release a sound. Now, the release of a sound takes some energy. So for instance, if you are very, very, very tired, right? Let's say you're very tired. In the morning, you just woke up and you're very tired and you don't have energy. If you have to speak when you're very tired, speaking is an act of releasing a sound, right? Through your vocal cords, through your mouth. It's an act of releasing a sound, right? That act of releasing a sound takes some energy. If you are very tired, it takes some energy. You will agree with me that it takes some energy to actually speak, right? Or even to snap your fingers, right? To do this, it takes some energy. If you're very tired, doing anything takes some energy. Even snapping your fingers to release a sound, right? Right. Now, the same thing applies with a ball. When a ball strikes the wall, a sound is released, right? A thud is released. When the ball strikes the wall, a sound is released. When a sound is released, some energy is released because it takes some energy to make that sound, right? It takes some energy to make that sound. There's a little bit of heat released as well, but that's very small. The main source of energy that you lose from having the ball make impact with the wall is sound, right? So because a sound is released, you lose some energy. Now, because the energy has been lost, the energy that you start off with, the kinetic energy that you start off with for this ball is not going to be the same as the kinetic energy that you end up with for that ball. Right. Now, remember, we said that the kinetic energy that you start off with, EK, before, for an elastic collision, the EK before should be the same as the EK after. This is if the collision is elastic. But if it is not elastic, then that is not equal. Those two are not equal. Now, why are they not equal? Well, remember what makes up kinetic energy. Kinetic energy is made up of mass and velocity of the object. Now, what has changed here? Has the mass of the object changed? No, the ball is still the same. The ball is still the same, right? It still weighs the same, it's still the same shape, it's still the same ball. It just happened to bounce off the wall. What has changed? The velocity of the ball has changed, right? The ball approached the wall with a specific velocity. It hit the wall, then it bounced off the wall with that specific, with a different specific velocity. So these two velocities are not the same. Since these two velocities are not the same, then it follows by definition that the kinetic energies of the balls are not the same. It's the same ball. The kinetic energy of the ball before collision versus the kinetic energy of the ball after collision is not the same. It is not the same because the velocities are not the same. And why are the velocities not the same? Because some energy was lost when the ball made contact with the wall. Now, since some sound was lost, some energy was lost. Okay, since some energy was lost, then the system overall lost its energy. Therefore, the collision is inelastic. Okay, so that is essentially what an elastic and inelastic collision are. Now, I want you to note something very important. Okay, remember we covered the law of conservation of momentum. Law of conservation of momentum. Law of conservation of momentum. The law of conservation of linear momentum states that in a closed system, right, we covered this in a separate video. In a closed system, the linear momentum is conserved or is constant or it does not change. Okay, you can say it in a number of different ways. You can say the same thing in a number of different ways. So the law of conservation of momentum states that the linear momentum in an isolated system is constant, right? But I want you to note that just because in a closed system the momentum is conserved does not it does not mean that the collision is elastic or inelastic. So whether the momentum is conserved or not does not influence whether the collision is elastic or inelastic. So for instance, we covered a video where we covered an example where we've got two cars approaching one another. Two cars approaching one another, right? This one is moving to the left, this one is moving to the right. They meet there and they collide, right? They collide. These two cars collide and they get destroyed like that, right? Now, if the collision was elastic in this situation, if the collision was elastic, what was going to happen is that these cars were going to bounce off one another. They're going to come here, collide, bounce off one another as if they're two tennis balls, and then just move away from one another with the same kinetic energy that they had, right? Or these two cars could be, if one of the cars is stationary, right? If one of the cars is stationary and this car goes and hits that car and both cars move at the velocity of the initial car, then the collision is elastic still, right? The collision is elastic, right? Because the velocity did not change. If the velocity of this one was zero, the velocity of this one was zero, and this one had a certain speed, this one had a certain speed, and the total speed of the cars after they collided, right, was the same speed as that car moving on its own, then this would be inelastic. But the momentum would be conserved, right? The momentum would be conserved. Notice that the momentum is conserved and the collision is elastic if the total velocity in the system does not change. It does not change. But, there's always a but, right? If, just do that. If, right, these cars are moving towards one another, right? Or even if these cars are not moving one another, let's just keep the scenario the same. Say this car has a certain velocity, this car on the left has a certain velocity, this one has no velocity on the right. It has no velocity. This one collides with that car and they move, right? They move to the right. Both cars move to the right, but at a different velocity. So this velocity and that velocity are not the same. Then the collision is inelastic, but the momentum is still conserved. Notice how the momentum is still conserved. So the momentum is not influenced, the conservation of momentum is not influenced by whether or not the collision is elastic or inelastic. The energy of the system, the total energy of the system, in this case, the total kinetic energy of the system influences whether or not the system is elastic or inelastic, whether the collision is elastic or inelastic. Okay, so that is what an elastic and inelastic collision is, and that is their relation to the law of conservation of momentum. Let's do a quick example to demonstrate this, right? I'm going to use that wall example again. You've got a wall, you've got a person throws a tennis ball. Let's say this tennis ball weighs 0.1 kilograms, right? And it is moving at a speed of, let's call it 3 meters per second. It's moving towards the wall, gets to the wall, hits the wall, bounces off the wall, and as soon as it bounces off the wall, it has a velocity of 2 meters per second. Now, is this collision elastic or inelastic, right? Is it elastic or is it inelastic? You can probably tell by just inspection, by just looking at this scenario, you can probably tell that this collision is inelastic. Why is it inelastic? Because the velocity after the ball has bounced off the wall is not the same as the velocity before the ball bounced off the wall. Therefore, the collision is inelastic. But if we had to prove that mathematically, then you would just say, okay, cool, so I've got my ball. My ball has a mass of 0.1 kilograms, and my initial velocity is 3 meters per second. This is the velocity at which the ball approached the wall. So the kinetic energy before collision, is equal to half mass is 0.1, v is 3 meters per second, then squared, right? If you punch this into your calculator, you will get an answer of 0.45 joules. This is your answer. If you punch this into your calculator, you'll get 0.45 joules. So this is the energy that your ball had before bouncing off the wall. Now, what about the kinetic energy after? Let's do that. EK after. Okay, so the kinetic energy after is equal to half. The mass of the ball does not change. It's still the same ball, so it's still going to be 0.1 kilograms times the velocity after was 2 meters per second. Let's just confirm that up there. There's 2 meters per second after bouncing off the wall, right? So if you do this calculation, you will see that the answer is 0.2 joules. Okay, that's 0.2 joules. Now you will notice that this energy is less than that energy. They're not the same. The energy before, the kinetic energy before is not the same as the kinetic energy after. Why are they not the same? Well, because we threw the ball hit the wall, it made a sound, right? The thud that the ball makes when it hits the sound, it made a sound. Since it made a sound, it takes some energy to release sound. So some energy was released to make that sound. Since some energy was released to make that sound, some energy was lost by the ball. Since it lost a little bit of energy, it got a little bit tired when it had to move back towards the person that threw it. So it moved back at a lower velocity of 2 meters. It started off at a velocity of 3 meters per second, and it moved back at a velocity of 2 meters per second. And therefore, the kinetic energy was reduced. Okay, and therefore, the collision, to answer the question, the collision is inelastic. Okay, and probably 100% of the cases that you're going to come across in real life are going to be inelastic. They're going to be inelastic. There's always going to be a sound that is released when two objects make contact, right? When two objects make any considerable contact, there will be a sound released. It could be sound, it could be in the form of heat. So for instance, friction releases heat. So sometimes heat energy could be released in a system. So it could be sound, it could be heat, it could be whatever. Some energy, some form of energy has to be released in order for your collision to be inelastic, and that's almost 100%, if not 100%, of the situations that you're going to come across in real life. Okay, so when you're seeing elastic and inelastic collisions, just know that for the most part, elastic collisions are theoretical, right? I'm not sure if they can be achieved in real life. Inelastic collisions are what you're usually going to come across. Okay, so that is what elastic and inelastic collisions are, and we might do a past example, or we might solve a past exam question in one of our next few videos, and we will also be covering impulse to continue with our momentum topic. Okay, see you in the next video. Till next time. Lesson number one, lesson number one. Lesson number one, lesson number one.